Hey, Portugal vs Croatia is tonight. Who you got?
$100 on Portugal for sure. Are you in?
Keep your money. I have a much better option.
What's this?
You'll find out when the match starts. Alright, your team is set to Portugal. It even lights up in the team's color. And my armband set to Croatia. Yeah, zap time.
Ow! What the is this?
That's the loser's punishment.
How the hell does this Armband even know the score?
Let me show you. To make this actually work, we need 3 core pieces. First, the punishment. As you just saw, we need a circuit that generates a safe but effective electric shock. Second, the data. We need a way to feed the live match scores directly to the device. And third, the brain. We need a microcontroller to process those scores and trigger the shock the exact second a goal is conceded. The core of this is a step-up transformer, just like this. It takes a low voltage input and cranks it up to a high voltage output that your body can definitely feel. I'm going with this smaller, weaker one because the goal is a harmless prank, not a hospital visit. But even with a smaller transformer, we need to strike control over the power to make sure it's 100% safe. We do that using PWM or pulse width modulation. Think of PWM like flickering a light switch on and off incredibly fast. If you leave the switch on for a tiny fraction of a second and off for the rest of the time, you deliver very less overall power to your load. And that's how you can control the brightness of an LED. Since our microcontroller is generating this PWM signal, it only outputs a weak 3.3 volts. We need to bump that up to 5 volts with enough current to actually drive the transformer. To solve that, I'm using this HW532 opto-coupled MOSFET module. It handles the power boost and more importantly, it completely isolates our microcontroller from the high voltage side. Now that the ZAP circuit is working, we need to make it smart. We need a way to feed it live match data. Finding this data was the hardest part. Standard APIs like API Football are great, but for an instant shock, we need to check the score every few seconds. Do that for a full 90-minute games and you'll instantly max out the free plan. But after doing some digging, I found a goldmine. It turns out ESPN has a hidden undocumented API. It is completely open, updates almost in real time and let us ping it every few seconds without hitting any paywalls. If you open it in your browser, you get hit with a massive wall of text. But this is just a standard JSON data. Don't worry, we can ignore 99% of it. We only care about a few specific lines. Here, we just pull out the unique event ID and the match name. Then we scroll down to find the home team. We grab their ID, their current score, and the hex code for their official color. Scroll a little further, grab the exact same data for the away team. And that's it. That's all the data our device needs to track the entire game. You can modify this link for other leagues or sports, but I've added the FIFA World Cup here for now. To act as the brain for the whole operation, I'm using the ESP32 Super Mini. I choose it because it's incredibly tiny, which is perfect for a wearable, but it still has built-in Wi-Fi. Programming the ESP32 to handle all this data took a lot of trial and error, but the logic is actually pretty simple. First, the ESP32 takes our SSID and password, connects to the Wi-Fi, and grabs an IP address. To get device ready for the match, I designed this web UI that is accessible through the device IP address. But IP addresses change, and I really don't want to hunt for numbers on game day. So I implemented MDNS. Now I just type zapband1.local into my phone's browser and our custom web UI pops right up. Since this is a 2-player band, I build a second band and set it to zapband2.local. You can build as many of these as you want by just changing the name in the code. This custom web UI hosted directly on the microcontroller. It's got 2 simple drop-downs, one for the live match and one for the target team. To get this data, the JavaScript sends a request to ESPN's public scoreboard API, parses the JSON, and listed exactly who is playing right now. The moment I hit ARM device, the web app fires the match ID, the opponent's team ID, and even the team's color back to the ESP32. The device is now officially armed and hunting for goals. From here on out, the code targets ESPN's core API by generating a specific URL that returns exactly one thing: the opponent's team live score. If this score goes up, it triggers the ZAP circuit for 500 milliseconds. The UI also has a disarm button. Clicking this tells the code to stop waiting for goals. The last button is test shock, that manually triggers the pain. There is a live status text at the bottom, so I always know exactly what the system is thinking. And to make the whole thing look extra intimidating, I mapped a 5x5 LED matrix to a dedicated state machine function. It has 5 visual modes. Matrix connected. Gives a quick green checkmark when the Wi-Fi connected successfully. Matrix offline. Shows a blinking red X if the Wi-Fi drops. Matrix arm breathing. Pulses smoothly in the target team's color while waiting. Matrix Zaps strobe. Goes absolutely crazy, flashing white and the team's color during a zap. And Matrix disarmed keeps it at a dim white. I modeled up a custom case to 3D print, but this isn't your average project box. Because the high voltage side generates so much noise, there are some design tricks baked right into the plastic. I'm throwing in an OLX LBC 3.1 power bank module, since this needs to be completely portable. The first trick to avoid high voltage noise is to connect all the power wires directly to the source. Once the ESP32 is powered up, I route pin 10 to the ZAP circuit and pin 21 to the RGB matrix. Before we install the MOSFET, we have to add a snubber. This completely kills the voltage spikes that the transformer generates. If you like this build, hit that thumbs up and subscribe so you don't miss the next project. I also solder a 470 microfarad capacitor directly to the MOSFET module's power pins. It provides instant surge current to the transformer, preventing sudden voltage drops that would crash the ESP32. One of the transformer wires connects to the 5 volts, and the other connects directly to the MOSFET module's load pin. I put these holes in the 3D print so we can just run the wires directly out of the box. Since they come off the secondary side of the transformer, draw the exact wire that delivers the zap. This is the RGB matrix that will display our device states. It mounts directly to the top of the box, and a piece of a diffuser goes over to give it a much cleaner look. Just like we did for the MOSFET, I solder another capacitor directly to the matrix power pins, and a 330 ohm resistor in series with its input pin. I'm powering it all with this 18650 battery so we can pull off our next trick. These batteries need a BMS circuit, so I connect the battery to the input pads. I solder 2 wires to the output to fit the power bank module. The trick with placing the battery here is that it builds a shield between the high voltage and the ESP32. Since its metal body is tied to ground, it perfectly absorbs all the high voltage noise. I also 3D printed this little knob so we can easily press the power button from the outside. To attach the pieces of the box, I use a snap fit design, so there is no need for any screws. These wires have to make direct skin contact to transfer the zap, so I attach these conductive foam pads right over the ends. Finally, we just loop a strap through the case so we can mount it right onto the arm. Alright, it's ready to go. The device armed successfully and turned green, and the test shock triggers the strobe exactly like it should. Let's try the zap. Nothing. Maybe I'm just too tough. But yeah, something is definitely wrong. After some digging, I found a design error. This module minimum input is 6 volts, and our power supply is only 5 volts. If we swap this resistor right here for a 10K one, that solves the problem, and we can drive it perfectly with 5 volts. So, now that you know exactly how this evil little Armband works, let's get back to the game.
Yes.
How? That hits very different when you aren't the one pushing the button. Damn it. I really should have just taken the $100 bet.